Hey everyone, and welcome to this explainer. Okay, so today we are tackling a total classic. We're asking the question, why is the sky blue? It's honestly time we look up and finally demystify the incredibly cool, basically invisible mechanics happening right over our heads every single day. Right, so it's literally one of the very first questions we all ask when we're kids, isn't it? If sunlight is white, then why on earth is the sky blue? I mean, it seems like a simple enough question, but the answer, it actually involves a secret spectrum of colors that is hiding right in plain sight. So today, we are going to be tracking the epic journey of a single sunbeam to find out exactly how this whole thing works.
Okay, let's dive into this. Now, sunlight might look to us like this solid, continuous white beam, but actually, no. It contains literally all the colors of the visible spectrum. And what's key here is the difference in how those colors travel. Take a look at the waves. Your colors like red, orange, and yellow, they have these long, lazy, rolling wavelengths. But if you look at the other end of the spectrum, colors like blue, indigo, and violet, they travel in much, much shorter, tighter, sort of choppy waves. Keep that in mind because it's absolutely crucial for what happens next. So imagine that light hurtling through the sheer vacuum of space. Out there, it is a perfectly easy, straight shot until, bam, it crashes right into Earth's atmosphere. All of a sudden, our sunbeam hits an absolute obstacle course made of literally billions and billions of microscopic nitrogen and oxygen molecules. And this invisible atmospheric barrier, this is where the magic really begins. And this brilliantly illustrates what happens next. When those light waves slam into that barrier, it triggers a fascinating physics process called Rayleigh scattering. It's actually named after a 19th century British scientist, Lord Rayleigh. And what Rayleigh figured out is that these tiny atmospheric particles scatter those shorter wavelengths of light, our tight, choppy blues, much, much more strongly than they do the longer, rolling red and yellow waves. It's basically like those short waves are hitting a microscopic pinball machine. Now, what's really interesting about this slide is, well, it reveals a bit of a biological plot twist. Think about it. If shorter wavelengths scatter the most, and violet actually has the shortest wavelength of all the visible colors, shouldn't the sky look purple? I mean, physically speaking, the sky actually is partly violet. It really is. But your eyes, well, they just don't care. See, human biology and solar physics are basically teaming up to filter out that violet hue. And it comes down to three specific reasons. First off, the sun itself just emits a whole lot more blue light than it does violet light. Second, our human eyes, the way we're actually built, we are biologically far, far more sensitive to blue light. And third, to top it all off, a good chunk of whatever violet light is there actually gets completely absorbed by the upper atmosphere before it even has a chance to reach us down here on the ground. So because of all that filtering and biology, what are we actually left with? A sky completely and totally saturated in blue. Thanks to Rayleigh scattering, that blue light is just bouncing around the atmosphere in absolutely every direction imaginable. And that is why, no matter where you look during the daytime, perfectly scattered blue light is reaching your eyes, literally painting the entire sky for us. But hold on a second. What happens when the sun goes down? I mean, we all know the sky certainly doesn't stay blue forever. When you change the physical variables, like the actual angle of the sun in the sky, the entire atmosphere canvas shifts and we get completely different colors. Let's move to and see how this builds step by step into a sunset. So, when the sun is setting, it sits super low on the horizon, right? This means its light actually has to travel through a much thicker, much denser layer of the atmosphere to finally reach you. And during this extended, much longer journey, all those shorter blue and violet wavelengths, they get absolutely exhausted. They scatter away completely before they ever reach your eyes. So what survives? Just the longer wavelengths, the reds, the oranges, and the yellows, which is exactly why the horizon lights up in those beautiful, warm colors. And honestly, knowing all this proves that our beautiful blue sky is essentially just a massive atmospheric illusion. It's an illusion that is so easily altered by weather or even pollution. Take clouds, for instance. Their large water droplets scatter all the colors completely equally, which leaves us with a white or gray sky. But then, if you introduce dust or smoke or volcanic ash into the mix, you alter the scattering entirely, producing some incredibly surreal, dramatic sky colors that look totally otherworldly. And to really drive this home, just look at that stark contrast between our everyday daytime experience here on Earth and an astronaut's view. Up in space, there's practically zero atmosphere, which means without those billions of air molecules to act as a barrier and scatter the sunlight, the sky appears completely,
pitch black. Even when the sun is shining right beside them, blindingly bright, the sky itself is totally dark. No atmosphere, no blue.
It really puts the whole thing into perspective, doesn't it? If the blue sky is just this incredible microscopic illusion of scattered light, how will you look at our atmosphere tomorrow? Stepping outside and looking up to see a vibrant blue ceiling, it is a uniquely earthbound privilege. So the next time you look up on a beautiful sunny day, just take a second to remember the incredible invisible physics dancing right above you. Thank you so much for joining me on this explainer, and definitely keep exploring.